Okay, so 1 second. I need to. This is 30 seconds, but otherwise you hear my echo if I want to start the SPICE. I have to pause it for a second.
Should I mute myself? Is it better?
No. You don't have to. Okay. Alrighty. So I wanted to thank everybody. Oh, I think for some reason my thing what happened to my video? I would like to welcome everybody once again to the online SPICE-SPIN+X seminar series that I organized here together in collaboration with Libers Mekia, Angela Wittmann, and Karen Abersusita in Duisburg. And this being collaborative research center SPIN+X, led by Martin Aslimar, Burkhard Hiller-Brands, and Matthias Klaue here in Mainz. As you know, this is a Zoom webinar. Please write the questions down or raise your hand, and I will promote you to ask the questions to the speaker. If it's something important during the talk, write it down and I will ask, but typically we will do it afterwards. And then with that, you can follow. So today it's a pleasure to us to have Nina Delter. She was actually one of the organizers of one of the SPICE workshops recently, and has moved to Caltech to be a postdoc for the group in the group of Gilles Raphael, and she's completed a PhD, very good PhD, with Professor Achim Ross in Cologne, and she's mostly interested in magnets and all things that you can do in magnets, particularly out of equilibrium. And with this, I would like you to please go ahead and share your screen, if you don't mind. And begin your presentation whenever you wish.
Yep.
And I will put up. Okay, perfect.
Okay. You can see everything?
Perfect. So go ahead.
Okay, great. Yeah, so hello everybody. It's a pleasure to be here, and thanks to Jairo for the invitation. So today I'll be talking about fractional topological charges. And of course, given my French background, I couldn't resist cracking an asterisk and obelix joke. But don't worry, the actual fractional charge we'll be discussing will be in magnets. And yeah, so with that, let's get started. So first, I need to thank some people without whom this work wouldn't have come to fruition. So my collaborators, Achim, of course, but also other people in the group. And so we just actually, the paper that I will be discussing just was published a few months ago, and you can find it here on the internet. So the structure of the talk is going to be quite simple. First, I will give you some background, math and physics background that's needed to understand what I'll be talking about. I'm going to try to make this quite gentle so that it's accessible to as many people as possible. And then I'll give you some concrete examples of fractional topological charges and magnets and see that they actually occur pretty naturally. And finally, in the third part, we will look at some of the properties that make these fractional charges interesting and different from their integer counterparts. Namely, we will look at Magnon scattering and the Aharonov-Bohm effect. Okay, so with that, let's get started with the first part, background. So let's start with a very simple question, which is, can we always, this is a maths question, can we always map a sphere to a plane? So they're both 2D surfaces. Can we map them to a sphere to the plane? And the answer is yes, you can always do that. And one way is by stereographic projection. So I found a nice YouTube video which illustrates this. I'm just going to play it now.
Or rather, this is a sculpture that illustrates stereographic projection. So stereographic projection is a map from the sphere to the plane. And the way that it works is you look at the north pole of the sphere and you draw straight lines from the north pole down onto the plane. Each such line hits the sphere once and hits the plane once. And so the map from the sphere to the plane is where does the line hit the sphere? That maps to where the line hits the plane. And why are we sitting in the dark? Well, straight lines are pretty well approximated by light rays. And so this is the light on my cell phone, which is a pretty good approximation to a point light source. And if you arrange the light at the North Pole, then the light rays effectively do stereographic projection. And these curves on the sphere are mapped to this straight line grid on the plane.
Yeah, okay, so that's stereographic projection. So it's very simple. You take every single point on the sphere goes to a single point on the plane, except for one point at the pole. So, for example, here it would be the South Pole, which goes to infinitely many points at the boundary of the 2D plane. And stereographic projection has a lot of other uses. So, for example, one of the most notable ones is cartography, as you can see here. But yeah, so quite a useful tool. Now, the opposite question would be, can we always map a plane to a sphere? And the answer is, well, no, you can't. Usually you can, but if you have a situation where your function has multiple values on the boundary, then you cannot map it back to sphere because, of course, well, how can you put multiple values on a single pole? So, okay, that was some maths intro. Now, how does this relate to physics? Well, we're going to be discussing magnetism. And in magnetism, you can always describe a magnet by a vector field M of R if you are dealing with a semi-classical magnet. So what does that mean? It means that your magnet is, so the spins which describe the magnet are varying on a very slow scale compared to the atomic scale. So here's our vector field M. So it has three components, 3D in spin space, but it's a function of 2D R. Yeah? So that's what we're going to be dealing with in this talk. And how do we determine this M as a function of R? Well, it's determined by minimizing something called the free energy of the magnet. So, free energy, okay. So in the very simplest case, you would have only one term in the free energy, which is called the Heisenberg energy. So that's given by this here. And basically what this tells you is we penalize variations in space of M if J is negative. If J is positive. If it's negative, on the contrary. Yeah. So, and basically already just by varying the sign of J, you can get different types of magnets. You can get ferromagnets or antiferromagnets. And also you can change the temperature and then you get like a ferromagnet or paramagnet transition. So we want to make this a little bit more exciting now, and we add some additional energy terms, which are chiral anisotropy or external B terms. And so we enrich the free energy to look to this form. Okay, so one thing we can do is add, so this chiral energy term. What is that? It's a term which breaks the inversion symmetry and also favors twisting. Yeah, so whereas before the magnets like to be anti-aligned or aligned, now they like to be at 90 degrees to each other thanks to this term. And this encourages the magnet to twist. So we get textures like this, like skyrmions or also conical magnets. So you can get a whole range of different phases just by adding this term. This term here is an example of an anisotropy term. So here we, for example, encourage the magnet, the z-axis for positive kappa u to turn away from the ez direction. And this would be an external applied magnetic field. Okay, so already by just varying D and J and also the applied magnetic field and the temperature, we can get a range of different textures. And I want to emphasize that what I'm showing here is also completely has been observed experimentally in many various different systems. And so the most common examples would be like manganese silicide or iron germanium and CSO. Basically, these are common examples of systems which host these so-called chiral textures. And they exist at a range of temperatures and also length scales. So yeah, we have a large zoo of magnetic textures, exotic magnetic textures to choose from. Okay, so the next thing we want to address is how do we quantify the amount of twisting that we have? So one very useful quantity we can define is this so-called topological charge density, which is given here. And so if you think about, so if you want to understand what this refers to, you just plot here I'm plotting the magnetization. And so basically, if you do some cross products, then you realize this is actually, this quantity here is exactly the solid angle element subtended by 3 non-collinear vectors. MR and M at R displaced by a little distance dx and M at R displaced by a little distance dy. And yeah, so with that, we now use this to define the overall, something called the topological charge, which is just when you take all these little solid angles and you integrate them. So you integrate of your whole plane and you add up all the little d omegas, and that defines you the total, something called a topological charge. And so this Q has some interesting properties. One is that it is preserved under smooth local deformations. So if you just deform your M at some point, and increase the d omega at some other point, you will increase it. And so overall, it is not affected. And also, Q is entirely determined by the boundary magnetization of your 2D sample. So with that, let's actually calculate Q for the texture we know, which is a skyrmion. So the brute force way to do it would be just to take your parametrization for the skyrmion, insert it into the formula, do some algebra, and work it out. And the second way, which is a bit more elegant, is just to visualize it. So we're going to use the tool we learned from a few slides ago, which is stereographic projection. And so we can see that basically when you map, because it's a single value at the edge, at the boundary, you can do stereographic projection and map this thing onto a sphere. And then, so for example, for an air skyrmion in particular, then all the magnetization vectors M are also parallel to the position vector so R. And therefore, the solid angle, so each individual solid angle corresponds exactly to the solid angle on the sphere. And so overall, when you sum it all up, well, you're wrapping exactly once around the sphere, so your topological charge is going to be 1. Here I put absolute value because it's actually -1 for a skyrmion, but yeah. And so now we want to use some useful properties that we know about Q to also calculate it for another skyrmion, which is the block skyrmion. And so we said Q is preserved under smooth local deformations. What does this mean physically? That means any deformation that you can do with a comb. So if you take a comb and you just comb the spins a little bit, you see that you can get from one to the other without any tears or without going through the surface. And so therefore, the topological charge is identical for both kinds of skyrmions. And actually, this argument is valued for any smooth magnetic texture which is single valued at the boundary. So any kind, it doesn't matter what's going on inside precisely. If it has a single valued M of R at the boundary of the sample, then the topological charge will always be an integer. So what about if your M of R is multi-valued? What happens there? So in this case, we cannot do stereographic projection anymore. But what we can do is just look at the boundary and plot all the directions of the spins in the spin space. Yeah, so you get necessarily a closed loop. And then you will notice that Q is basically just given by the ratio of the area inside the closed loop over the total spherical area, which is going to be smaller than 1. And so that means that for multi-valued, so whenever your magnetization is multi-valued at the boundary, then Q is necessarily fractional. So that concludes the background part of the talk, and now I'll give you some examples of fractional topological charges which can actually occur in magnets. So the first thing we will consider is a so-called fractional vortex, and the free energy of the system is given by this here. So we have Heisenberg interactions, we have also an applied magnetic field in the Z direction, and the uniaxial anisotropy also in the Z direction. And so the competition of these two terms here, the two potential terms, means that the spin, the magnetic field makes the spin wants to align with Z, but the anisotropy makes it want to go away from it. So there's a competition, and as a result, the spin will lie on a cone with this angle. Sorry, my office has some annoying. Yeah, the light turns off randomly. So yeah, so the magnetization will lie on this cone, and that means that so if we have on the boundary the magnetization lying on the cone, and inside the smooth interpolation, then we can calculate the total topological charge. It's just going to be the area of the spherical cap divided by the total area, and it comes out to be this number, which is so in the special case that you have no applied magnetic field, B0 equals 0, then you have exactly Q equals a half, and this is known as a meron. And in the case that you do have some finite field, it will be smaller than that. So that's all very nice and well, but it's unfortunately quite hard to realize experimentally because it requires you to really be able to control all the boundary of the sample. So it's not that easy. I want to highlight an exception, which is in the case of the meron. Actually, it turns out that the bimerons are a common instability for skyrmions to decay into. So if you take a skyrmion, you lower the magnetic field, then the first instability that it will go to is that it will decay into two merons. And the sum, each meron has a charge 1/2, so overall the initial topological charge of 1 is preserved. Okay, so let's go to something which is maybe a little bit more easy to access experimentally, which are cubic magnets. So what are cubic magnets? These are magnets where you have some cubic anisotropy, and this is given by this term here. So the cubic, okay, so basically we can vary kappa c as a coupling constant, which can be either negative or positive, and depending on the sign, either the spin vector m will like to be parallel to the mx to the mx and y and z axes. So in the case that kappa c is positive, or it will really dislike it. And so this you can see here if you plot the potential. So here we're just plotting this part, and yeah, the spin always goes to the minimum of the potential, which is in both cases opposite. So okay, so we have these domains that form. So in the case, for example, kappa c is positive, these will be in the z, x, mx, and z and y directions. And so these will just form naturally in a magnet, right? And whenever you have, so we know that we need to have some area covered in spin space, which means we have to have at least 3 or more domains, right? If you have 2, the interpolation between them is a line, but if you have 3, then some kind of area can be some area in spin space will be covered. And so this is precisely what happens. So here we have so for example here, if you look at this figure, we have 3 domains. So here in the x direction, y direction, z direction, and the spin smoothly interpolates between each along a straight line in spin space. This is, by the way, guaranteed by additional symmetries that the line is straight. And in between, so in the region where the 3 domains meet, you will have some trapped topological charge, which is shown here. And if you calculate how much, what is the total charge trapped here, then it will be exactly minus 1/8, because the lines are straight. So it is a quite quantized value. And And you can do exactly play the identical game with the opposite sign of anisotropy. And now you will have, so because the easy axes are now given by 1, 1, 1, which are the corners of the sphere, you will basically have, so when you have 4 of these meet, you will cover exactly one face of the cube in spin space, and so overall your topological charge is the area of one face over the total surface area of the cube, which is 1/6. And again, topological charge is concentrated where the 4 domains meet. And so this is a completely generic system, right? And we expect in general that in any magnet, cubic magnet, you will have different domains forming. So we expect that this should occur pretty naturally in cubic magnets. And I want to highlight that also, yeah, so there's another way of viewing this, which is a non-abelian vortices. And yeah, look at this paper if you would like to see how they have done it. So it's quite interesting. So the next example I want to show you is with our old friend the skyrmion. So as we discussed, the skyrmion has total charge 1. What about if we try to break it down into smaller pieces? All right. So here's our free energy of the skyrmion, and we added, so it's exactly the usual free energy, but we added a little bit of cubic anisotropy as well in this term. And what we're going to do is we're going to try to make the skyrmion decay or explode. So what do we do for this? Well, we just take the stabilizing field and turn it off suddenly. So, and then let's see what happens. Okay, so as you see, when you turn the field off, the skyrmion becomes unstable and decays or explodes. And because we have some cubic anisotropy, the magnetization likes to align along certain axes, which are in this case is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that is why you get also this characteristic square shape. And basically, the argument is the same as for the previous slide. Wherever you have 3 domains meeting, you will get some trapped topological charge, and this is what happens at the four corners of the square. And in each case, you have basically the equivalent of two such cases. So it would be this one and the one on the bottom, and so overall you get each one of these has exactly with the charge of 1/4, and this is also exactly quantized. And I want to just quickly also mention the case where you make kappa c opposite signs. So in that case, now the easy axes are these. We also did the same experiment. So we turn off the magnetic field at time 0 and see what happens. And now it's not as neat as before, because your background magnetization, which was previously also one of the easy axes, is no longer an easy axis. So, and what we see here is that the system gets confused. It has 4 possible directions into which it could decay, and it doesn't know which to choose. So initially it's very kind of messy. And over time, as you wait longer and longer, it settles down a bit. And so you get more clear domains forming and topological charges wherever 3 of, in this case, it's 4 of these meet. And then you can start again checking that charge is conserved. And so if you count these, you will always see that there are exactly 6 more purple ones than orange ones, which means that overall you have the initial, yeah. So the different colors correspond to plus or minus 6. So overall, you still always conserve the initial charge of -1. Okay. And now I want to show you, so previously what we've talked about so far, these fractional charges have one negative thing about them, which is that they are not easily mobile. So because you have to change a lot of spins, you have to change a macroscopic number of spins to move the texture. So in the last example I will give you, I want to show you a texture where this is not the case. And so what we'll look at is something called the domain wall within a domain wall. So this is our system here. And we have, as before, some Dzierżinski-Murray interaction, and we also have now some some cubic anisotropy, easy plane anisotropy and applied magnetic field. And this means that we have 4 energy minima, which are at the 4 corners of a square, and with a slight MZ component also because of the applied field. And if you take 2 opposite corners and you ask how will the magnetization between 2 such domains interpolate, you actually have two choices. So either the red or the blue here. And this is, so you can see here, either we go via the spin here in the middle is opposite sign. So either we go via this direction or via this direction. And then you can ask the question, okay, what if I take 2 of these different domain walls and bring them together? Well, then in that case, of course, you will have, so you will cover then, you will be spanning some of this, some spin area, yeah, because now you have a closed loop. And so overall, you will get, and this is here highlighting how much of the spin surface you will span. And then you can calculate how much Q you have trapped in there. And in this case, it's about minus 0.6. But the cool thing about this system is that, so this Q is now not quantized to a fraction, but can be controlled. So you can, depending on what you choose for B0 and kappa P, you can make this, you can change you can make the easy axis have a larger or smaller MZ component and then change the Q. And the other cool thing is that you have, because you have basically a translationally invariant system, as soon as you move away a little bit from the topological, from the defect here, so from here upwards and from here downwards, you only need to change the spins in the vicinity of this defect to move the defect up or down. So basically we have a defect which is mobile in the y direction by a microscopic number of spins. Yeah. So this makes this defect a little bit different from the previous 2, which I discussed. Okay, so with this, so I've given you some examples of fractional defects, and I would like to move on to the last part of the talk, which is about what makes these defects cool. So, okay, so we've discussed topological charge and seen how it's basically quantifying the twisting and it's an invariant quantity. But why is it interesting from a physics perspective? So one thing which makes it interesting is that it affects small particles like electrons or magnons, which are traveling through the magnetic texture. And how does it do that? Well, basically, electrons and magnons, when they travel through a magnetic texture which twists, they also have a spin axis, and their spin axis always likes to align with the local magnetization M of R, right? And so as a result, as they travel, if they travel through a texture which is twisting, then their axis will also twist, and this means that they will pick up a Berry phase, which leads to emergent electromagnetic fields. So now the next slide will just be explaining how you get this for magnons. So what is a magnon? A magnon is a disturbance, a spin disturbance around the local magnetization, right? So we can, here I'm going to show you some maths for how we can describe this. So basically, we have our spin m, yeah. So m is a function of r, and it is parametrized here by. So basically, the magnon will be any disturbance. So that means that it's any disturbance in the plane perpendicular to m. Okay, so this will be parametrized by the vectors E plus and E minus, and E3 is parallel to the actual M, so without any disturbance. And so mathematically, you can write this like in this way. So here, U is a 3x3 matrix consisting of the 3 orthogonal vectors, and M dash would be the vector in the plane. So so it would be the vector when you have basically when it's aligned with the z-axis. So and you have A and A star are the creation and annihilation operators of the Magnon. So, which here I wrote with, usually you would put daggers, but here we wrote with stars because we're dealing with semi-classical physics. And so just in order to make sure that you still have the spin commutation relations preserved, you need to also impose a Poisson bracket on A and A star. Okay, so we have our magnetization in terms of the A and A star. And the term which we need to look at to obtain the emergent magnetic field, and which I'm talking about, is the exchange energy. So we take our M, we substitute it into there, and then we just do product rule. So the partial derivative here will act either on U or on M dash, so you get 2 terms, right? And you can rewrite this by taking one U out. And so it takes then the following form, and which is a form familiar to us from just a particle traveling in a magnetic field, because it has, so we can write this derivative operator as a momentum divided by h bar, and then that means that the second term here is nothing but the there's a mistake here. Well, anyway, that this term here is the gauge field. So I should also highlight here that we have now picked. So we take only the 1, this is a 3x3 matrix, right? When you do U inverse times the gradient of U, it's a 3x3 matrix. But we only care about the diagonal components because we only care. At the end, we want the field theory in terms of A and A star, and we only care here about the number conserving terms. So the Bogoliubov terms, A squared, A star squared, we don't care about this so much. Okay, so that is here our gauge field, and when you actually calculate it, putting in these vectors E plus, E3, etc., then you get this formula, and from that you can then use the definition of the EM tensor. And we're interested in our case only in the magnetic field. So if you calculate it all, then you get something which looks like this. And you can also compare it to the topological charge and realize it's exactly the same. So we now want to rewrite this in units of the flux quantum, which is given by this. And so in units of the flux quantum, Bz is just 1/2π times topological charge. So if we now integrate over all space to get the total flux in the z direction, we have the total flux of Bz, then we get that the total flux is just going to be 2 times the topological charge, right? Because Q had a factor of 1/4π here, so that would be 2 times that. So any magnon traveling through a twisting magnetic texture will experience a flux of 2 times the total charge of the texture in units of the flux quantum of the magnon. Note that, so what I've shown you is here all for magnons, but you can do an exactly identical derivation for electrons, and then you will get, in this case, actually, it will differ by a factor of 2, so it'll be just Q. So an electron sees half of the flux that the magnon does. Okay, so this, what I've shown you so far, it applies to any kind of topological charge, integer or fractional, but we want to see actually what distinguishes a fractional charge from a topological one, right? So can we design some kind of experiment where we see different behavior of fractional phi? And the experiment we're going to do is Magnon scattering. So idea is very simple. You take a system and you start pumping in some magnons, right? So how do we do this? We take, for example, here. So I've taken here the last defect from the previous section. So the domain wall within the domain wall. And we take all the spins on the, for example, the left boundary, and we start wiggling them in time, right? And so when you do that, basically you're pumping magnons into the system, which will have some kind of momentum k depending on the rate at which you wiggle them. And they are related via the dispersion relation of the magnet. And so when the incoming magnons arrive on the defect, this acts like an effective magnetic field, so it will scatter them. So basically, if the magnon comes in with momentum k, which is parallel to x, it will be scattered into another direction, which is not necessarily parallel. And you can calculate the change in momentum of the magnon. And of course, if the momentum of the magnons changes, that means that they will produce a net force back on the topological defect. Yeah, that's Newton's third law. And the force is exactly given by the total rate of change, but minus the total rate of change of the magnons as they get scattered. And then you can ask, okay, so there's a force produced on the defect, how will it move? And for this, you can solve something called the Thiele equation, which is given here. So basically, this tells you that v is the velocity. V is the velocity of the defect, and this here is the Magnus force. This is a dissipation force. This is an applied external force. So from the scattering of the magnons. And so we're interested in this system where we have a very long. It's very long in the y direction, and so much longer than x, and that means that also if you calculate the dissipation matrix, which is a 2x2 matrix in this case, basically one term dominates all the others, which is the dxx term, and so you can this equation it simplifies a lot, and you can solve it to give you that the defect should hardly move in the x direction and move in the y direction with this velocity here, so proportional to the applied to the scattering force Fy. And so let's see if this works in practice. So here on the right you see a simulation where we did exactly this. So we pumped some magnons on the left, and as you can see over time, the defect does move in the vertical y direction. So I should highlight this little deformation you see is basically happening at the rate of the pumping, so omega. And yeah, the slow diffuse motion is what the slow motion upwards is what we're interested in, which is Vy. Okay, so now we want to see actually how does this Fy depend on k, on the momentum of the magnons, and on the fractional and on the flux phi. Yeah, because we want to see the influence of fractional flux. So for this, we need to know a little bit more about the scattering force. And so how is this calculated? Well, so it's quite a simple idea. I'm just going to quote the result, but not derive it. So we have so we have magnons being scattered. So we have each magnon has momentum h bar times k, and magnon current is how many of these magnons are hitting the target per unit area per second, right? And then we need to multiply by the scattering, the perpendicular scattering cross section, which is telling you, okay, what proportion of these are gonna cause it to move basically upwards. And the scattering cross section has been calculated already, so a few years ago. So Aharonov and Bohm predicted it in 1959. to be this value. I should also stress there's actually two limits that you need to look at. So basically, it depends if your Magnon wavelength is large or small compared to the size of the defect. Because if it's if this result here applies in the limit where the Magnon has very large wavelength compared to the size of the defect, and in the other case where it's very small, it gets deflected very little, and then it's the classical limit. So the Aharonov-Bohm, as discussed, calculated this already in 1959. And actually, however, people disagreed about this for years. There were basically a lot of controversies. And finally, it turns out, yeah, you need to do some things carefully, but you do arrive at this result. Yeah, so there are basically two limits for sigma per. And the other thing that we need to calculate is so before I say, yeah. So here, so one thing that we notice immediately is if your Q is not integer or half integer, then sine 4 pi Q will be a finite value, and this means as K gets very small, this will become very large, right? It will be singular in 1 over K. Whereas if you do have integer Q, then this thing will go to 0. So we say that integer and half integer Q are gauged out. So we're interested in how the force varies as a function of K. And if you now substitute this in there, you'll see that the singular K cancels with this K. So all the behavior at low K will be determined by what happens with the Magnon current. And this is something we can also calculate. So in the case where you have absolutely no damping, you would just expect this to be related to the group velocity of the Magnon. But we do have damping, so we need to include that. And again, I haven't included the details of the derivation, but you can calculate this. And then you get this formula here. And so because of because of this presence of this exponential factor, as we go to smaller and smaller K, there is a gap in the system. So the top goes to some finite value, and the bottom it goes like K. So actually, overall, this goes like e to the -1 over K, which means that it goes to 0 for very small K. So there's some problem with the work anyway. So unfortunately, the f of y drops to 0 as K goes to 0, even for fractional charge. So instead of that, we need a smoking gun to distinguish between fractional and integer charge. So we can't use this, but what we can use is the fact that there is a sign change between as a function of K in the scattering cross section. If you choose your Q to be in a certain range, yeah. So if you choose 2 times Q to be between half and 1, and then this factor will be negative, but this one will be positive. And so they have a different sign, and so we expect sigma to change sign as a function of K, and also as a result f of y. And that means that if your force changes sign, also your velocity of the defect should change sign. And this happens only for a fractional Q in a certain range. Okay, so let's see if we see this also in practice. And here I have a plot basically where we take our defect, which has okay, so it doesn't say here, but so the charge of this has 2Q equals 0.7, right? So we are definitely in the correct range. And when we plot, so here we change the frequency of the Magnons, we change the K. And at some point we see that the defect, so first things first, the velocity does drop to 0 as expected when we go to the gap. And then also as we increase the frequency or K, at some point we see a sign change in the velocity, which means that we do have this is the signature of the fractional the fact that the defect has a fractional charge, which you would not have if it were like a skyrmion or something like this. Yeah, so with this, I'm basically done. So what I try to show to you today is that you can quite easily get magnetic textures with fractional topological charge. They should be easily detectable in experiments as well. And one of their interesting properties is that they singularly scatter low energy magnons. And yeah, and then you can see manifestation of the Aharonov-Bohm effect. So for the future, I think it would be cool to take some of these defects and like stabilize them. For example, with this skyrmion, exploding skyrmion, these defects, they keep expanding, but it would be cool to find a way to basically make a bound state of them and say, then start doing games like driving those bound states, but now fractional charges. And just to show you, so this is what we have for bound state of 3 integer charges, in this case, different 3 skyrmions. But yeah, how would such a state here, if it were stabilized, respond to driving? Would it be faster, slower? Would it change directions? And yeah, so that's one possible idea. And now I'm very happy to take any questions.
Okay, thank you. Thank you very much. So now we are open for questions. If you want to raise your hand, and I will promote you to the panel if you like. But let me start it by asking a few things on slide 25, particularly when you're looking at the analogy of this effective magnetic field, the orbital magnetic field that one gets from this gauge field, yeah. So as you rightly say, this gauge field itself is in fact a matrix. It's not, you cannot directly at that moment call it a vector field. In what regime can you, and of course, the off-diagonal elements, as Ahim and others have shown, could be related to the Losinski-Maria and some other terms. What is the regime that you're assuming? Because here, of course, you're making a map into where, effective field on the spinless electrons. Now here you're having this thing that you're going to scatter from as an effective magnetic field on textures that also themselves are determined by the strength of this exchange, the spin-orbit coupling involved. So what are the different limits that you expect these to work the best?
So I'm guessing, do you mean like in which limit do all these approximations work?
Yeah, so essentially you're looking at only the diagonal terms. You care only about not the off-diagonal terms, for example, as you mentioned. This would only work in reality, actually. I don't think you can just say, go ahead.
So I think one thing is that you're neglecting the Bogolubov terms, I'm guessing. This a squared, I mentioned that. So yeah, if you in reality, Magnon number is not conserved, unlike electrons, right? Because there are bosons. So it's not really correct. And the other thing that we haven't also considered is the fact that the magnons will scatter from a texture which is itself also changing in space. So the whole derivation basically afterwards, when we then because the way that the scattering cross section is calculated is they assume that we have just some flux in the middle and then everywhere else is uniform, So it's very easy because everywhere else is just a ferromagnet and you don't have to worry about which is
a magnetic field from that,
which is not true. In reality, if we have a fractional charge, then we must have, because the magnetization is multi-valued, we must have actually a spatially varying magnetic field. And so there will be a factor. The formulas I've shown are simplified. There will be actually a factor which is k-dependent, coming from the scattering of magnons from this spatially varying domain walls, for example, in the case of the domain wall and domain wall defect.
But
so,
are you making assumptions about how large this domain wall will be relative to the wavelength of the magnons, or which limits are you considering?
Yeah, so for this reason, you do have to, if you want to do it precisely, you cannot ignore it, which we haven't done because it's so difficult, like it's a difficult problem. But if you wanted to do it in full glory, it does count. The lower the k, the more it matters, because then you have the same it varies on the same scale as the domain wall, which is slowly varying. So yeah, you're completely right. It's oversimplified in the small k limit. And the other limit, I think it's correct when k gets large. No.
Okay. So I don't see any questions on the here. Maybe 1 second, see if there's anything written. I don't see it, but let me ask another question then in this front. So you've shown that very nicely that you can actually change this velocity of this the motion of these impurities. Yeah. This is in here you're doing it by pumping just the Magnons. Yeah.
Yeah.
In a system where you would actually maybe have a gradient of temperature or something that you can actually drive instead of just the pumping, because in here the pumping would work, I assume, best with an insulating ferromagnet rather than a metallic one. If you wanted to do it with a thermal gradient, have you estimated maybe to think of what it would take to see the thing?
I haven't estimated, but it's a good idea actually. Yeah. Need to do that.
Okay.
Thanks.
This one would be nice to see. This the fractional ones, but the smoking gun, as you say. Now this is in California in the West.
Yes, it's a well.
Gun control there. Okay. So with this, I think I don't see any direct questions yet. Please contact Nina directly if you have any questions on it, particularly the ones that are watching it afterwards, as I usually schedule yourself to watch. And she's, I think, easy to find in Caltech and in the group of Jill Raphael, as I mentioned. And thank you once again, Nina, particularly for waking up very, very early. We have to all realize that there's a 9-hour difference, and she started all excited, woke up at 4 in the morning to be ready for this. So we really thank you for that. Okay. Yeah. So thank you, Nina. Have a great rest of the day, but I think you should have a shorter day since you woke up so early. You should go have a swim or something. Okay.
Yeah, actually, the pool is already open, so.
Good. All right. Thanks a lot. Thanks, everybody. And we'll see you next time.